Welcome to another video explaining the universe using the particle model. Well, today's video is one in this series I call Ask Particle, Not Quora, and this one is on superconductivity. Actually, it was my subscriber 635574, that's his name. He asked a couple of questions, and I'm listing them here, and I'm trying to respond to them. He asked his first question, do you have a model for how superconductivity interacts with magnets and the magnetic levitation? Well, when he asked the question, I didn't know much. I've been looking at it, hoping to get closer to being able to talk about it at least. I'll have to come back to this. His second question is, why do some materials become superconductive at low temperatures, and that basically locks in their magnetic field? So I'm going to try to go ahead and address that question. Superconductivity there's a theory called the BCS Theory. In 1957, John Bardeen, Leon Cooper, and John Robert Schrieffer proposed a theory to explain why materials lose all resistance to become superconductors at their critical temperature, called BCS Theory. The main idea of the model is that it describes the formation of pairs of electrons in the conductivity process. These pairs of electrons are called Cooper pairs. And here's how they describe the formation of Cooper pairs. According to the BCS theory, as one electron passes by positively charged ions in the lattice of the superconductor, the lattice distorts. And this is a very clear picture of the lattice distorting due to the presence, in this case, of two electrons. Electrons are negative. The lattice is presumed positive because apparently they've lost electrons. And as the electron comes by, it distorts it by pulling it together. And it creates a high positive charge center here, the electron being attracted presumably to this and this one to there, causing an electron pair or Cooper pair. A couple of things that the particle model would have difficulty with this is, number one, the electron has, in our case, is a G1 particle, has no charge, and as a consequence, the positive ions that are in the lattice are not positive either. Second problem I have is it's just maybe an artist's conception of the drawing in any case, but that's a lot of distortion for just one or two particles to cause the lattice to distort that much. Probably done for emphasis, but to me, the drawing is exaggerated. The two electrons form what is called a Cooper pair, which is a stable state. As the electrons move through the lattice, they remain coherent, that is, together as they pass through the lattice unimpeded. Yeah, well, they're forming pairs. I don't know if they have any direct evidence of Cooper pairs, but and they're stable. I'm not sure. They're stable because in semiconductors, these things apparently have to be stable, and they move through the lattice unimpeded, with no explanation of why. Why is that unimpeded? Well, let's ask the question of why are some materials superconducting? And I found this link, and that link has a description of what semiconductor materials are. Superconductors and superconducting materials are metals. It could be metals, ceramics, organic materials, or heavily doped semiconductors that conduct electricity without resistance. And of course, that's at lower temperature. In that same link, they drew this chart, not a real chart, it's just to show the point. You have a material that's a non-superconductor, and you have one that is. On the left is resistance. Temperature is high here, gets lower until it gets 0. That's in Kelvin. C is the critical temperature. And a normal material that is not a superconductor, as the temperature drops, the resistance drops. Resistance is dependent on temperature. That's one of the things I've not included in my equation. Don't have much data to deal with it, but at some point that should happen. But for a superconductor, it behaves the same way. As the temperature drops, the resistance drops until it gets to the critical temperature. And then it drops off sharply, at least according to this chart. And admittedly, this is a generalized chart, but so I had to look at some specific ones. Well, before I did that, he asked, why are some materials superconducting? And this is from the same link. And this has temperature. On the left, it has when these were discovered, the year from starting early 1900s out to 2010. And these are all the materials that are superconductor or become superconducting. And the three of kind of are interesting down here because they're simple, just one single compound. There's lead, mercury, and niobium. And you have to get way down in temperature for them to become superconducting. And over time, they've worked on more because if they can get it working at higher temperatures, which this is a much higher temperature, then you can get the advantage of this levitation that is talked about with superconductors. Well, it's kind of interesting to note that you would have thought that with a simple structure like these three, that they would more easily gotten to be a superconductor, and yet these more complex ones that they just throw together, of course, sort of like Edison throwing together filaments until he gets the right one. They throw these things together, and they're more complex, and yet they become superconducting at a higher temperature. Interesting list on the right shows you what some of the temperatures relate in terms of reality. This temperature, just slightly above Kelvin, 100 degree Kelvin, is the night on the moon. If you're on the dark side of the moon, it's that cold. Liquid nitrogen here. The surface of Pluto here. Liquid neon, liquid hydrogen, liquid helium. Kind of interesting. But why are some here? I never found any specific answer. They just give you examples. Much like materials that hold charge or a positive and negative charge. There's a list of them called the triple electric effect. And there's just a list. And we know it does it. Rarely do you find an answer to this question, why some materials do and some materials don't. Tough to answer until you understand the atomic structure and what's going on. Why would this be so easy up here and this so difficult? Well, I was looking at the Mercury because it's a simple one, and I was trying to verify this D, this thing that looks like a singularity. And sure enough, this chart that I got from this link looks like it has data points, which really tell us that, yeah, it kind of behaves this way. It drops so quickly, I don't see any data points in here. And then there are some other charts you can see. This is YCBO, yttrium, carbon, boron, oxygen. It's called YCBO, although I didn't find this on that other chart. But you can see that it doesn't drop so sharply. The sharp knee isn't there. But it does drop. It changes quite dramatically, and then it's conductive in this temperature range. So, it does happen. This knee has never been explained in what I've looked at. Why does it change that way? Don't know, but it does. Well, one of the things that always interests me is how you measure this. And I found this link, and there's a nice article on how to measure, and they give you a simplified schematic. Some of these, if you look at test equipment to do measurements, it looks really classy, well built, and you can't even see this so much, this circuit. But they describe the circuit. They talk about the source, a constant current source or a power supply operating in current limit mode. The output should not exceed a half an amp in order to protect the circuitry. Basically, although this looks like a battery, they use a DC supply with feedback control that allows only a half an amp to flow out and all the way back, and they measure it back here. They can see they're at a half an amp by measuring it there. A digital voltmeter with 0.01 millivolt resolution, that's 10 microvolts, to measure the voltage drop across the voltage at probes 2 and 3. So just inside of these probes, they're measuring the voltage drop across there, while the main current's going this way. Then they have a container of liquid nitrogen deep enough to completely immerse the 4-point probe device. That's the 4-point probe device. This is kept at room temperature. This gets dropped in. They watch it cool. They can monitor the current and voltage. They can even record it on an automatic, certain meters. You can feed it right to your laptop and get the thing recorded. And they record it while the temperature is going down, and then they can pull it back out and record it as it warms up. And nonetheless, when it finally gets down to a low enough temperature and is superconducting, they measure 0 volts. Now the resistance is, simply Ohm's law, voltage divided by current. Current's a half an amp, voltage is 0, resistance is 0. That's how they get it, but they can plot it like those curves that I just showed in the previous slide. Well, the particle model analysis, I've done this for circuits. This is the way I deal with it. It's a matter of G1 particles flowing around and through the circuit. A is designated the number of G1 particles entering the power supply, and this is supposed to be the current limiting supply. Normally, a battery adds G1s. And so I have a value B here. You have a parallel circuit where the B1 splits to B1 and B2. This is very high impedance, but if it's going to measure a voltage, you're going to have a loss here. You have loss here. Even at low ends, you probably have an occasional loss, but when it reads absolute 0, you're expecting C1 to equal B1. Same with this path. C2 should equal B2 if you have 0 loss. Remember that there's a direct correlation in the particle model between the loss of G1s as they pass through the resistor to the voltage drop. So you expect no loss across that, no loss of G1s. So how do you get losses of G1s? Now, you remember the G1s interact 3 different ways with any object. First way is they pass straight on through. Have a free path, they go straight through. Second one is they hit and scatter. That's equivalent to the voltage drop, as well as they can get trapped. They enter, but they get trapped. They stay in the resistor. It's a loss regardless. It's a voltage drop. Now, if you're going to have a zero loss of G1s, most of the G1s must have a clear path and not hit any part of the superconductor or get trapped by the superconductor. That has to happen. Things aren't absolute in the particle model. There's always the possibility that you're going to have some extraneous loss. A system can't be perfect all the time, but it can be reasonably stable for a long time, and some of these incidental hits and traps might not be detected by your meter. Okay, so how do you get to this condition? Well, the atoms of the superconductor must have no vibration. And of course, that's what you expect when you get all the way down to 0 Kelvin, although I don't think they get to 0. So I say absolutely almost no vibration. It's almost impossible to stop them from vibrating, which would cause some incidental loss of G1s, maybe not detectable. The G2 force field must be very stable. The G2 gravity that surrounds the whole test circuit and the superconductor is what's holding it together, and that's the G2 force field inside helps guide these through a path. So it must be stable, and generally you would expect it to be, although you could bring other strong electromagnetic forces nearby, and who knows what would happen. But that if the force field changes in any way, it's going to cause the motion of the atoms, and you're going to get some incidental loss. But you expect that it's going to be very stable. All spurious G1s must be eliminated. I say must be. Most, again, as usual, most of them spurious. What I mean by sometimes they don't come in initially. Initially, they come in at a different angle when you want them to go straight through. They come in down, or they're coming in up. Those will hit rather quickly and be gone, and I call them spurious G1s. Will be eliminated, again, most of them. Then most, if not all, G1s will have a stable path when you get to these conditions. Why the BCS doesn't explain the open path? There's a lot of open space in this material. Especially with lead and mercury and niobium, YCBO are much more complicated. How do you get a nice, smooth, straight path through that and get it to be superconducting? But this is the only thing that the particle model can say until anybody has direct evidence of how electrons flow through or the G1s flow through. Sharp drop-off, no explanation that I can find anywhere. And I don't know what happens. Some dramatic geometric change in the structure of the superconductor changes such that, boom, it drops off. Not at all clear. Instrumental, are you getting down to the level of the instrument problem? Some of the curves don't drop off so sharply, they come down rather slowly. So it's not clear why the change of direction on that, no explanation. Conclusion, why do some materials become superconductor at low temperatures? I don't think science knows why some of those materials are superconductor and some not. Just like we don't know why some materials hold charge and some don't. The BCS theory and the particle model have ideas. They have their idea about Cooper pairs. The particle model suggests you have electrons that have no charge that move through at speed c through the open space, and that being as superconducting, the lack of the vibrations and the stability of the forces help guide them through. Neither one of us have explanation, I think, of the drop-off, the sharp drop-off. Well, these are the questions that 635574 asked. Didn't address this one. Tried to address the first half. Going to try to look at this. I looked at what is he asking me here about the fact that a superconductor at low temperature that basically locks in their magnetic field. Couldn't quite find that, but what I did find was something called a persistent mode. An electromagnet, being super cool, has what's called a persistent mode. And it has an interesting, the particle model has an interesting answer to that question. And I'll continue to look at levitation to see if I can get more of an understanding of what's happening in the first place and then how the particle model might explain it. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the particle model explaining more of the universe using the particle model. Thank you for your attention.